looking at, we were going through CX gate at morning, and I wanted to say that CZ gate today morning we have went through CZ gate also. CZ gate is same as that of C naught gate only. I have explained the truth table also. The code is same for both the CX gate as well as C naught gate. So what I feel is you can go through, everyone can go through CZ gate on their own because it is same as C naught gate. All the code are same, just we need to change. We need to know the truth table and the matrices. That is what the difference between all the gates. And we can now quickly move on to the swap gate. We have a lot of things to cover today, so let's do the calculations side by side. So we have something called swap gate. Swap gate. So as the name suggests, and before that, yes, controlled Y gate and controlled H gate are homework. This is good, easy only. Just try it out from your side. It is easy. Control Y and control H gate. Nothing has to be done there. So why I've given that easy thing as homework. Yes. Next is quantum swap gate. So in quantum, as a name suggests, swap means nothing but we are interchanging the qubits. First qubit, what are the qubits? We are using first qubit and second qubit. And since we are using only two qubits, we are interchanging the two qubits and no conditions are given for this. There is no controlled swap gate, that is in the multi qubits only. As for two qubits, there is no controlled for two qubits for the swap gate. Okay, so I haven't kept it in the slide. I don't keep it in the slideshow mode because we'll be parallelly doing work on the Jupyter notebook, as well as we'll be using the notepad also to solve. So why I haven't kept in the slideshow mode? I haven't kept in the slideshow mode. Okay. Um, Truth table. So swap is nothing but, just now we have explained, it's nothing but we are interchanging the qubits. If you have, as in the truth table, you can see 0 0, you will get 0 0, and for 1 1 you will get 1 1. For 0 1 you have to swap as 1 0, and for 1 0 you have to swap as 0 1. It is self-explanatory, this truth table is. And for swap gate, we will just quickly get the truth table for this. Sorry, not truth table, the matrix. So we have Q0 and Q1. So 0 0 0 1 1 0 1 1. So if we apply swap, what will happen? You will get same 0 0 1 0 here. You will get 0 1, and you will get same 1 1 here. So to get the matrix for this 0 0, today morning I have explained 0 0 means 1 0 0 0. If you have any doubts, you can go through morning session notepad. It is in the front side. I've written in the solid in the front, and I'm just writing it quickly because I remember it. 1 0 means you have 0 0 1 0. 0 1 means 0 1 0 0. 1 1 means you will get 0 0 0 1. So this is the truth table for swap. So this is the truth table for swap gate. Sorry, not truth table. The matrix for the swap gate. Okay, and yeah. So this we found this matrix for this. And when we go to the circuit diagram, we can see that both are interconnected. This X mark is nothing but an interchanging of the qubits. So in this, I will explain this. If it is it's going from Kashmir to Kanyakumari. Okay. So yeah. If you have pi and you have psi over here, this is pi. Sorry, this is psi, psi. This is pi. Okay, and Yeah, X mark here. Yeah, this is nothing but interchanging of the qubits. This is how we represent the swap gate, and for this you will get uh, pi. We will get psi, because why? Because you can ask me why this is interchange, because it is a swap gate. Swap gate means interchanging of the qubits. Okay, so this is quite easy. Now we can quickly move on to the um, Jupiter. Qubits are interchanged and no controlled qubits are present. We have already mentioned this, and we are creating a variable called QC underscore SW and quantum circuit. In this, we have given two qubits here, so I've written two. So indexing start from zero. So we have written as zero. So in this circuit, it is displayed as Q0 and Q1. Next is we are interchanging the we are putting, I mean, applying X gate to Q1. Why? Because we have already said, I've already said that Q0, I mean, by default the it is by default the qubits are gate 0 only. In order to, if you see, if you have 0 0, and then if you interchange, if you use swap gate for that, what will you get? You will of course get 0 0 only. So there is no use of applying swap gate, right? So for that reason only, we are just flipping the gate, I mean flipping the qubit by applying X gate, poly X gate to Q1. So what will you have when see Q0 and Q1? Okay, so Q0 is gate 0 by default, and we're not applying any gate 0 for this. And for Q1 we are using poly X gate for this, and flip the gate, so it will become 1. So what is the output? Will what is the output? The bit so after applying the C swap, sorry, not C swap, swap gate, we will get as 1 0, है ना? Because we are flipping the gate, sorry, flipping the qubit after applying the by applying Pauli X gate, right? So this is what we get. In the Little Indian, it will be again 0 1, because it's Little Indian will be ZQ1 and Q0. Okay, so our state vector will be, so what is the state vector? Our state vector will be 0 0 0 1 1 0 1 1. In this you will have 0, and then for 0 1 you have 1, and for 1 0 you have 0, and for 1 1 you have 1. Okay, so you have to apply a complex value for this, plus 0 point j plus I will write it neatly over here. So this will be 0 plus 0 into j, comma 1 plus 0 into j, comma 0 plus 0 into j, comma 0 plus 0 into j. So this is how the state vector will be. And what is the q sphere for this? Q sphere will be we have what is the q sphere for this? Oh, oh. Mm, what is the q sphere? We have said it is 0 0 over here, and 0 1. Sorry, it's not 0 1, it's 1 1. Okay. It, okay, so it's 1 1 for here. So 0 1 over here and 1 0 over here. Since we got 1 0 now, after applying Little Indian, so it will be pointing to this part. Okay, so this is how you represent q sphere, and we don't want unitary operator. It is same as what we use, and it is reversible, so there's no use of solving the unitary operator because it is reversible. So you can see in we got 1, and what we solved is also what we solved here is also 1, and you can also verify that in the q sphere, so it is 0 1 only. And unitary operator, it is same, the code is same. If you check the C6 gate now, it is the code is exactly same. Only thing is, in this first part now, you just have to change the variable name and then apply the qubits according to it. And if you want to flip the gate, you can flip the gate, otherwise you can just try it out. It's like a try and error. Okay, code, everything is same. You don't have to worry too much about it. And for quantum simulator, you need to use measure, or you can use measure all. We have discussed about this also in the morning session, CX gate. So we can just quickly go, and we will get the simulator. We are running this for 1,000 times. We are running shots equal to 1,000, so we are running for 1,000 times, and we are getting 0 1. After running 1,000 times also, we are getting 0 1. So 1,000 times we ran the simulator and we got 0 1. 1,000 time also we got 0 1 only. So there is no random measurements. We got 0 1 only exactly. Okay. So this is all about quantum swap gate. Now, morning we were discussing Bell states. We can quickly discuss about this also. So Bell state, we are what is Bell state? Bell state means we are applying. We need to have. We need to get the state an entangled state. That is the reason why we wanted to why we are using Bell states. Okay, in order to get the Bell state, you need to apply H gate and CX gate. This is mandatory. You can ask me why we are using it, but because even I don't have an answer, because this is how quantum computing is. We have to use H gate and CX gate to get this Bell state. And another reason why we are using H gate is H gate gives a superposition state. That is the reason why. Another reason why we are using Bell states. Another reason is I don't know. Even no one knows that, because only the founder people who have invented this Qiskit knows why they kept like that. For something na, for if you ask a lot of if you will get a lot of doubts, why this is like this, why this is like that. For something you don't have an answer. This is what I realized. For everything we can't find an answer in physics. We have to accept something as it is. At least we will get a peace of mind, I can say you. So I this is that is how I became. So I am saying you to follow this also. Okay. uh, and then we are using q, and then we are calling the variable qc underscore bell dot draw, and then we are giving mpl. We already discussed why they are giving mpl, because if we don't give mpl, we will get in black and white state. We are giving mpl, so why we are getting this circuit very beautifully. And then in the bell state, we are applying h gate, adamat gate to the 0th qubit, and then we are using 2 qubits for the bell gates. For the bell state, we are using two qubits. For the first qubit, you're applying Hadmat gate. So by q0, we have Hadmat gate in the q0, and then for CX we are using 0 and 1. 0 is nothing but control bit, and you can have target bit. You can also have 1 0 also. If you have 1 0, the result will change. I have just kept 0 1. And density matrix same. Bill state, everything is same. You have to same as that. You have to keep the backend as a state vector simulator, and then you are executing the result and then storing it in the variable, and then you are getting the result, and after getting the result, you have to print the result, and then you have to plot state city. And then why we are using result, because only in result the execution is value is stored in the result variable. Okay, so we will get a 0.70. 0.707 is nothing but 1 divided by root 2. 1. Why we are getting 1 divided by root 2? Because Adamat gate gives superposition. It can be either. I will explain this. Okay, so Adamat Adamat gate gives superposition. Okay, in last before session, on volunteer would have taught about Adamat gate. It gives superposition. So for it will be 0 plus 1 divided by root 2 for 0 kit 0. For kit 1, it will be 0 kit 0 minus kit 1 divided by root 2. Since it is 50, so 50%, no, I will write like this itself. It is easy. Okay, so 1 divided by root 2 into kit 0 plus 1 divided by root 2 into kit 1. Okay, so So there is 50-50 chance. 50% it will be in the q0 state, 50% it can be in the one state kit one state. Same way, 50% it will be in the kit 0 state, 50% it will be minus this state one state kit one state. Okay. So by we are so 1 by root 2, you if you take na value, it is 0.707. So why we are getting 0.707 for this. Okay. I think this is self-explanatory also, since we have already uh, solved a lot of gates for this. So if you solve like this, 0.707, we get 0.707 for this one, for the first part and the last part. So why in 00 and 11 we are plotting like this? Yeah, okay. And the second graph, we don't have anything because it is a complex number, and we don't use complex number in this, so it is empty. Okay. And then we are solving q sphere, since we got output as 0 and 00 and 11 0 0, so it will be in the bell states. See, in earlier now, if you noted, for a q swap, sorry, a q quantum swap, or cx gate or zz gate, for anything, your q sphere, you will have, it will be pointing towards at least in only in one direction. Okay, or 0 1, or 1 0, something like that only. But in but in Hadmard gate na, but in the bell states, the q sphere will be both. Why? Because it is in the superposition state, it is in both the states. We are not measuring, we are not measuring, so why it is in both the position, है ना? So that is the reason why we are using Hadamard gate. This is Q sphere for bell. Okay. And then yes, unitary operator. It's for these things we don't even have to touch the unitary operator. Let the Qiskit do the work. We don't have to work. If we sit and think why this is like this, then we will go crazy for this. We don't have to worry about unitary operator. Everything is explanatory. We have seen a lot of example from today morning itself, so not to worry about unitary operator. And yeah, we have to measure now QASM. For QASM simulator, we need to measure. So when we measure, it becomes probabilistic to deterministic. If we use measure, the quantum state, which is in the superposition state, will collapse to the one particular state, and we will get the randomness of the output. Okay, we will explain this. We will see this. The same code we have copied on the first, the bell state itself. From here, we have copied. Uh, we are not using measure all because we need to know the probabilistic value. We are not using measure all because we just need to know in how many states the bell state is in. Like we are just measuring the probabilistic way. We are just measuring the probable values, probable ways that qubits are in. Okay, so in this quasum, we are just collapsing those states to a particular state. That is why we are using measure. And then same code is copied, and then we are using barrier. So why we got this barrier, this vertical line, and then we have also explained why, what is 0 comma 1 and 0 comma 1. 0 goes in 0 and 1 goes in 1. And you can also write output equal to mpl. This is one of the method. I have shown this. Yes. And in the first line, QC bell, this is the variable name, and quantum circuit 2 comma 2 is 2 quantum 2 qubits, and you're storing this 2 qubits in the 2 classical register. This is what is explained in the first line. We have also seen this in CX gate, same thing only, same code, same, everything is same. Shots equal to 1000, same. In multi-qubits, we will find different counts every time we measure. So why we are running the circuit multiple times. If you execute the circuit multiple times, you will get different random number of outputs. When I share this notebook now, you can run this code multiple times to see The circuit, in this the total counts for one state is for, if we ran for 499 is nothing but we ran the circuit for 499 times, and we got 11 kate 11 state. In kate 11 state is 499 times. It's in kate 11 state is for 499 times, it's in 499 times. Okay, and kate 00 is 501 times. When we ran the circuit 1000 times now, so for 499 times we got 11, and for 500 times we get 00. If you run the circuit now again, this value might change. So why we have to keep running the circuit multiple times? When I share this Jupyter notebook, you can just run this code and see, you will be, getting random outputs. So this is how what build status. Next we are going to multi-qubits. Multi-qubit means 3 qubits. Okay, now we are going to CCX and CC naught. CC means control to control NOT gate. It is basically 3 qubit, and the main condition is first and the second qubits are control qubits, and third qubit is a target qubit. And what is the condition? Condition is first and second qubit should be one, and if first and second qubit is one, it will flip. So third bit will be flipped according whether it is 0 or 1. Okay. Yes. Now we will see the truth table matrix and circuit diagram. And see, in the truth table you can see that the last two rows now you can see first and second qubit. I will just write it and show it quickly. We will complete this also. It is very easy, same like CX gate only. Only thing is we have added another qubit. That is the only thing. No need to worry too much about it. Oh god, this line. Okay. CCX or CC not or Toffoli. I don't know what is Toffoli, the meaning of Toffoli. I will search and see if you want after some time. Or maybe the name of a person or anyone. I don't know. Okay. So 110. I will write neatly a little bit. Okay. So Q0, Q1, Q2. You're 110. So after applying CCX, we will get as 111. Q0, Q1, Q2, because first and second qubits are 1 1. So the third qubit is flipped to 1, and next is 1 1 1. It will be 1 1 0 because the first qubit is flipped to third qubit. I mean, the target qubit is flipped to 0 because first two qubits are 1. Okay. It is same like CX only, and the truth table is the same asset of CX only. I don't want to do this long calculation because it is too much hectic to do. We have a lot of things to cover. Another of the volunteer has to take the universal gates also, so this is very easy to get. Okay, you just have to do. I'll just show quickly only one qubit. You can just go through another one. Okay, so I will just show how do we make 0 0 1. So for 0 0 now, we have the qubit as 1000. We have to put the tensor product. For 1, what is 101? For this, if you compute, you will get 0 1. Wait a minute. 0 1 1 2 3 4 5 6 7 8. Why it is 8? Because it is in 2 to the power 3. 2 to the power 3 is 8 states it is. When you increase number of qubits, dimension increases. Uh-oh. Okay. So remember this, it is very important. This part is very important. Because 2 to the power 3, so why it is 8 states? Mm. Okay. We will be going to the Jupyter notebook and see what is happening. So in this, we are applying Xgate. Same we apply to the CX gate also. Why we are applying Xgate? Because we have to flip the bit. If we flip the bit to 1, we will be able to do the CC not gate operations. So if it is 0, Q0, Q1, Q2, okay, I will quickly explain this. So Q0, Q1, Q2. I've applied after applying X gate. After applying X gate, we got 1 1 1 because the bits are flipped to 1. When we apply what CCX, what do we get? 1 1 is there. The condition is satisfied, so it will become 0. So we'll get 1 1 0. So what is the state vector? 0 0 0 0 0 1 0 1 0 0 1 1 100 101 110 111. Another important thing, we have got 110, but what is the little Indian system? This is Q0 Q1 Q2 na, it will reverse. So what it will be? 0 1 1. We should not forget this, otherwise we will get a wrong answer if you attend any exam. Always remember, Qiskit always works in little Indian. Okay. So it is 0 plus 0 point j. 0 plus 0 point j. 0 into j. 0 plus 0 into j. Q 0 1 1. We have got 0 1 1 output. So we can write it as 1 plus 0 into j. So 0 plus 0 into j. 0 plus 0 into j. 0 plus 0 into j and 0 plus 0 into j. So this is what our output will be for the state vector. Okay. For um, Q sphere, we will see the Q sphere. Q sphere is a little bit on the tricky side. Q sphere, we have seen for 2 qubits is very easy. For 3 qubits, it will be little bit different. Okay. I will keep this is a dotted. It means it is multi-qubit. Okay. So above we have 0 0 0. You won't find this anywhere. I think I don't know whether you will find this in Qiskit or not, but I'm writing it 0 1 1 1 1 0 1 0 0 0 0 1. Here it is in this part you have 100. No, not 100. Sorry, it's not 100. It should be 0 1 0. This should be 1 0 1. So we got what output we got 0 1 1. So how so from this part it will I will differentiate and show this. So it is like this. Okay, it points like this. Okay, the same you will get in the Q sphere in Jupyter notebook also. See, we got 0 1 1. Same thing we also got in Q sphere. You got this 0 1 1. Okay, the same thing we also solved right now. Unitary operator is very tedious for taking this. No need to worry about it. And for quantum simulator, same code. We just have to use measure all, and then we can use barrier also. If you use measure all, you will default get barrier. You don't have to worry. Or if you want also, you can use it. If you so this is the um, circuit after using measure all. Same code, we have to get the backend simulator to Quasm simulator, and we are running it for 1,000 times, and we're just getting the result. And if we run 1,000 times, we get 011 as the output. This is what CC not gate is. Okay, I hope this is clear. Very easy, similar to CF gate only. Just doing self study is enough. What I feel. Next is Q swap, quantum C swap gate. So swap we have already seen just now. Swap means interchanging of the bits. C swap means controlled interchanging of bits. Okay, so what is control here? What is the condition here? Control means it's like a condition. So what is the condition to swap the bits, qubits? It should and one another thing is you should always say qubits. Bits is for classical computing. We are studying quantum computing, so we should always try to mention it as qubits. Okay, so first qubit should be 1, and second and third qubit will be swapped. We are using 3 qubits here, and first qubit should be 1, so that next second and third qubit will be swapped. We can just quickly solve the truth table. Truth table is very easy, where 100 from 100 you will get 100. I'll just write it down, no problem. um any doubts as of now? I'm audible, na?
Yes, you're audible, ma'am. You're
Yes,
Oh,
audible.
ma'am, you're audible.
okay, so I'm just keep on speaking, so I thought no one is replying, so I don't know whether I was audible or not. Okay, guys, thank you. Right now, we have quantum C swap. Okay, cut truth table. Oh God, why this went so much? Okay, this is let it be a cheat sheet for you, so I'm writing it almost neatly. Okay, please try to please adjust if something is not good, but I'm trying my best to write very neatly. Okay, yeah, Q0, Q1, Q2. I don't want to write this 00011 because all these for these first four states now, you don't have any swapping happens, because uh, in order for the swapping to happen, you need to have the first qubit should be 1. So we don't have to consider the qubit which starts with 0. So I am skipping that, I'm writing directly. Okay, 100, 101, 110, and 111. Okay, so after applying CZ swap, what will we get? Q0, Q1, Q2. So first is the condition is satisfied. So even if is swap the gate, you will get the same only. For 1 also you will get the same thing. For 101 only, it will be changed to 110. It will again, this will be flipped to 101. Okay, so the matrix is also like self-explanatory only. Okay, you have to just for first four states now, it's diagonal, but for the last three, I mean for the seventh for the sixth and seventh row, for 101 110 only, the bit flip happens now. I mean, sorry, not bit flip, interchanging happens now. So which column? Sixth and seventh. 1, 2, 3, 4, 5, 6, and for sixth and seventh column only, you will have interchanging of the qubits. So for remaining all the columns, everything is same. This is also self-explanatory, very easy. So no need to worry about this matrix. Also, we have solved a lot of matrix. Okay, so yeah, for swap gate, we have seen this X mark as interchanging of bits, and then this part is like connecting Q0, Q1, and Q2. So this is also easy. Now we can move to the notebook. Huh. So same, you're defining a variable, and then you're putting the quantum circuit inside it. You're giving 3 qubits, and because it is 3 qubits, we are dealing with 3 qubits. And then you're applying X gate, Y X gate, because we just have to flip the gate to keep the Q0 should be 1. If the Q0, so we will just solve this quickly, okay? Q0, and for Q0, Q what is this? For Q0, Q1, and Q2. For Q0 and Q2, they have applied X gates. Let us confirm. Yeah. So what is the? It will be 1 year. It will be 1 year. It will be 0 year. So this is Jupyter notebook. Jupyter explanation. Okay. So after applying C swap, what will we get? Q0, Q1, Q2. What will we get? 1 1 0. So what is, how do we represent in little endian? Q2, Q1, Q0 now. So it should be 0 1 1. Okay, we can just quickly solve the state vector. State vector is 0 0 0 0 0 1 0 1 0 0 1 1 100 101 110 111 1 2 3 4 5 6 7 8. Yeah. So for this, we it is 0 plus 0 into j, comma, and 0 or 0 0 1 is also 0 plus 0 into j, comma, 0 1 0 is also 0 plus 0 into j. This one is 1 plus 1 0 into j, because this is this, comma, 0 plus 0 into j, comma, 0 plus 0 into j, comma, 0 plus 0 into j, comma, 0 plus 0 into j. So this is our state vector. Okay. Next, we are going to Q sphere. Q sphere. What did we get in the Q sphere? We got 0 1 1 now. We just quickly draw this diagram, and then say it as over here, and then over here, then over here. So here you have 0 0 0. You have 1 1 1. Here you have 1 0 0. Here you have 0 0 1. 0 1 1 0 1 1. Here you have 1 1 0. In here you have uh, 0 1 0. Here you have 1 0 1. Since it is 0 1 1, it is pointing to this direction. Okay, this is our Q sphere is the same thing they have explained it here. Okay, so we got 0 1 1, same, you can compare it. And Q sphere we got 0 1 1, same answer. And unitary operator, self-explanatory. And quantum simulator, we are just want to measure it. If we use the, if we have to again put quantum simulator running for 1,000 times, we get, for 1,000 times also we get 0 1 1 only. Okay, so our QASM simulator is over. Now all the qubits are over. Now we are quickly moving on to superdense coding. I will explain the superdense coding right here, because presentation I will, you can read it on your own. I will quickly explain it here. Okay. So superdense coding is an algorithm. Okay. Very easy. First point is it is used for quantum communication. We are using this for quantum communication. And main purpose, no, also we cryptography. Another use is cryptography. Second one is, second point what we have to remember is, if we need to send two classical bit strings. We can send it in the computer by using only one qubit is involved. So that is only one qubit is used to send two classical bits. Now the $1,000,000 question is how? Okay, that's what we are going to see. First, we there are 3 points. First, we need to prepare bell states. Second is encoding information. Third is decoding the information. Okay. Why we are using? First, we can explain bell states. Why we are using bell states? Just now we have gone through bell states. What before that? Bell states we are using because it gives entanglement. All this hard work is only for you. Gives entanglement. Okay. So this is the first point why we are using bell states. You can ask me how entanglement happens when we use when we use what gates? Do you remember? H and C naught. If we use these both gates together, we get entanglement. I hope you remember. We just now discussed a couple of minutes ago. If you don't remember, no problem. You can just revision as needed. Okay. In bell states, now you are having two part. You're having, I mean, we are having two people involved. We can start. We can say that you are having two people. One is sender, another one is receiver. I can name the sender as Alice and the receiver as Bob. In quantum mechanics, we refer Alice and Bob a lot. This is how we say sender as Alice and receiver as Bob. Okay. So we can have this, I mean, the Q for Alice now, we can name it as Q0 and Q1 because we are involving two people means nothing but two qubits. Okay. To put it in a very easy way, we are just explaining it in with an analogy as we are involving people here. So Q0 and Q1 is nothing but sender and receiver. They are nothing but Alice and Bob. Can take like that. Okay. So we are first creating a bell state. Okay. So Q0 is we are applying Hadamard gate to Q0. Why? You can ask me why you're using Hadamard gate to only Q0. I mean, Q0 means with first qubit. Why? Because who is the sender here? Alice. What we name Alice as? We can. Alice is only sending to Bob, na. So why we need to put Admart gate for her for Bob? We need to put Admart gate for Alice only because she's the one who's sending, right? So we need to put Admart gate for the sender, and then we need to put X gate Sorry, not Xgate, Cxgate. Sometimes, no, if tongue is slippery, please correct me. Okay, H gate, and this is C naught gate. Okay, so we have so this together, H gate and C naught gate together, we form a bell state. So this circuit created a bell state. Next step is to encode the information. Encoding info. Okay. Most important is okay, encoding the information. If you have four different ways. I have mentioned that you are sending two classical bit strings. The two classical bit strings can be in four combinations. What are those four combinations? 0 0, 0 1, 1 0, 1 1. Okay. So if you want to send 0 0, you need to apply identity matrix. Identity matrix is nothing but 1 0 0 1. I will erase it and write it 0 0. We have to apply identity matrix for this. Okay. Next is, if you need to send 0 1, this is a classical bit string. This is the message you're going to send. Okay. Classical bit string is nothing but the message you're going to send. 0 1, you're applying Z gate. So we will get 1 0. So Z gate is identity matrix is 1001. I'm just writing the matrix format for everything. Now I'm just writing the matrix format so that it's easy for the for our computation. Okay, there are a lot of steps involved in the upcoming portions. So Z gate, poly Z is represented as 1 0 0 minus 1. 1 0 is, we if you want to send the 1 0 message, we need to use X gate, poly X gate. See, this is this 1 0 0 1, all these are the classical bits. This classical bit is nothing but the message which we are going to send. Okay, I will also write as message. These are all message which we are going to send. Message or classical bits. Okay, and then this is Z is 1 qubit. I said na, we are sending two classical bit using 1 qubit. That 1 qubit is this X gate is 1 qubit. If we send 1 0 message, we are using X gate. If you are using, if you are sending message as 0 1, we are using Z gate. Okay, why we are using Z gate for 0 1 and not for 1 0 is, this is this is how Qiskit is. This is how Superdense coding is. We don't have an answer for this. Okay, this is how they have created, the founders have created it. Okay, for X gate is represented as 0 1 1 0. Okay, next we are sending 1 1 classical bit. How do we do it? 0 Z into X will get. For this now, we will do computation. For this, we need to apply first we need to apply X gate, then followed Z. We will just say it as Z into I, something like that, but don't confuse it. So I haven't written anything for this. Now we will do the computation. Okay, just let be a little bit focused. This part is very important. Okay, if we send 0 0 message, or we can say it is a classical 2-bit string. By default, I will also mention here, by default the Bell state is in 0 0 plus 1 1 divided by root 2. Okay, so if you write 0 0 plus 1 1, I don't want to write divided by root 2, but I'm just writing it so that we don't have to confuse it. So if you want to send 0 0 message, you will get the same answer, because we are using identity matrix now. That is the reason. So we will get the same Bell state only, what we gave input. Next, 0 1. We send 0 1. So the default Bell state is 0 0 plus 1 1 divided by root 2. Now we are applying. So if you want to send 0 1 message, I've said, if you want to send 0 1 as a message, you need to use Z gate. Okay. So what is Z gate? 1 0 0 minus 1 now. Q1 Q, this we have to like write like I'm just writing for remembrance purpose, Q1 and Q0. This is little Indian based. Okay, please don't confuse. If you apply, and then we are applying Z gate to Q0 only. Why we are applying to Q0 only? Because Q0 is the sender. Q0 is Alice. Alice is sending to Bob. So why we are applying Z gate to Q0? So when we apply Z gate to Q0, what will we get? The condition for Z gate. If you have 1, it will be minus 1. So 0 0, it will be same. I will keep minus at present. It is plus only. I will, okay, let me write plus. And in this now, this this Q0 is 1. Henna. Wait. So the qubit here is 1. Q0 is 1. So it will become minus 1. 1 will become minus 1. This is Pauli Z gate condition. So it becomes 1 1 only, but the bit is changed. Sorry, the phase is changed to minus. So it will become minus divided by root 2. Okay. Next is 1 0. We are sending 1 0 message. For this, we are applying X gate. X gate. So this is the default one. 1 1 divided by root 2. So this is Q1, this is Q0, Q1 and Q0. If we apply Z gate, sorry, X gate, apply X gate to Q0 only, what will you get? If you apply Q0, if you apply X gate to Q0, what is the condition? Condition for Q0. 0 becomes 1, 1 becomes 0. Okay. So it becomes, so when you apply xk to q0, what will you get? 1 huh, you will get 0 1 plus 1 0 divided by root 2. Okay. Next is 1 1, means you have to apply um, zx both. Okay, you have to apply zx k to q0. First we can apply x gate. First apply x gate. It should be from right to left. Okay, right to left, don't confuse. Right to left is nothing but we have to we just have to go from have to if you have this kind of combination zx gate, you need to come from right side to left side. That is what I mentioned as right to left. Okay, so what will you get in this? If you apply x gate, you will get 0 1 plus 1 0 divided by root 2, and then you are applying z gate. What will you get? Minus 0 1 plus 1 0 di- um, sorry, 1 0 divided by root 2. Okay, this is what we got. So we can draw the circuit diagram. Q0, first we have applied x h gate, and then Q1 is there. This is Alice, this is Bob. Okay, we are sending we are applying ADMAT gate, then we are applying X gate, so CX gate, and then Alice is sending message to Bob. For example, she is sending X gate 1 0. We can, okay, so Alice is sending 1 0 as a message. So 1 0 means it is Pauli X gate. Na? So I'm applying here, and then what do we get? Yes, sorry. And then I'm just applying a barrier over here. Then we will have C not gate. Okay, till now this is what we have found it till now. Let it be like this. After decoding, we will finish the whole circuit. Okay, it's better to go step by step. Now it is decoding. Now it is decoding the info. Okay. So what is decoding the information? Decoding means, see, for encoding, um before that I will explain another thing. Quantum gates are reversible. Okay, reversible means to create entangled state, we use H and CX gate. In order to de-entangle the state, we can use same H and C, but first we need to we can use CX followed by H gate. CX gate followed by H gate to de-entangle the state. Now we can finish the circuit. Q0, H gate, Q1, you have this one, and then this, and then you're applying. I'm just giving 1 0 as information. So I'm using X gate here. Then in this part, we are applying C naught, and then we are again applying HUD gate over here. Okay. And then we will get the output. So this is how the old circuit looks like. So this part is the first one, this is the second one, this is the third one. This part encoding, this is decoding. All part is decoding, and then this is decoding. The we are applying the and we are de-entangling the state first. Entangling and decoding. This part is entangling and tangling and encoding. Okay. So this is how the circuit looks like. For example, I'm just decoding. I will take only one example and finish off this example. I'm for this now. Alice is sending. This is Alice. This guy is Bob. Okay. So we am sending 1 0 message. So for 1 0 we are applying X gate. So I'm just decoding here. Okay. So 1 0. How 1 0 is represented? We have just now solved 1 0 Q01 plus 1 0. I'm just quickly writing it. The time is getting up, so I'm just quickly solving it. So when you apply HK, just a second. 1 0 0 1 0 1 plus 1 0. Okay, I'm right. So now, no, I'm applying C naught to de-entangle the state and decode. What will I get? C naught. See, this is Q1, Q0, Q1, Q0. What will I get? So we have to apply C naught gate. Applying C naught to Q0. What will we get? We will get 1 1 plus 1 0. I didn't write root 2 because let it be used for some other time. Okay. I'm just keeping it to easily explain it. Now we are applying H gate. Okay. To Q0. Okay. So here it is Q1, Q0, Q1, Q0. You can write it as in tensor product. You're applying ADMAR gate to Q0 plus 1 tensor product. We're applying ADMAR gate to Q0. And what do we get in this? Gate 0 minus gate 1 divided by root 2 plus 1 tensor product of Okay, 0 plus gate 1 divided by root 2. So what do we get in this? We get 1 0 minus 1 1 divided by root 2 plus 1 0 plus 1 1 divided by root 2. Okay, so we have root 2 denominator same, so we can add the numerator and then we can take the denominator outside. So you have 2 1 2 gate 1 0, right? So we can write it as 2 into 1 gate 1 0, and then we can cancel this 1 and 1 because minus 1 plus 1 1. So we get it as 2 divided by root 2 into 1 0. Okay, how can we solve this? We can write it as root 2 into root 2 gets we get 2 na, so we can write it in this way also. 2 we can write 2 as root 2 into root 2. Root 2 into root 2 is equal to 2. We are applying this condition. We can remove uh, huh, okay. So root 2 into root 2 equal to 2. We are applying this condition. And then we have 1 get 1 0 here. So this and this is cancelled. So root 2 into 1 0. So what Alice sent? Alice uh, Alice sent 1 0. Bob received 1 0. She used X gate for this. Okay. So we got, this is the decoding part which I've shown you. Okay. Other part also you can check, but just to know, I've calculated one decoding part. Okay. So this is what Superdense coding is. Now we can quickly go to the code. Now we are just importing the libraries, and then we are using the functions. For this we need to have a little bit of background in Python. As I've already mentioned, for first step to create a super dense coding is we need to create the bell pair. How do we create the bell pair? We use H gate and CX gate to form the bell pair. Okay. So and QC is nothing but the name of the qubit. I mean the name of the circuit, and A and B are just two arguments. And for A is the first qubit and B is the second qubit. Okay. A is for Alice and B is for Bob. You can take like that. And this is here we are creating the bell pair. First we are creating the bell pair by using H gate and CX gate. And H gate we are using for H gate we are using for 0th qubit. Here 0th qubit is represented as A. After that we will call the function name. Okay. So this is the step for creating the bell pair. And then we need to encode the message. QC is nothing but the variable name QC, and qubit, what qubit you are sending, and then message, what message you are sending. For example, message equal to 00 means pass means nothing. Pass is nothing but a value. It's like a function in Python. Pass means whatever input you give, you will get the output the same thing. We don't have to do anything. Okay. So that is what pass means. You need to have a little bit of background in Python to understand this. Elif and if else, these are very easy. And then we are giving condition. If elif condition for this, elif message equal to 1 0, then we need to apply X gate. We have just solved all these things. Okay. 1 0 means you are applying X gate. 0 1 means you're applying Z gate. Okay, so 1 0 means you're applying X gate, and if you're sending 0 1, then you have to apply Z gate. Okay. And then one word means you're applying Z and X gate both. If you don't see any message, it will be invalid. Sending 00. It's very self-explanatory. And decoding part, we have seen QC is nothing but the variable name, and A is like Alice and B is Bob. So we are applying CX gate in the reverse order. For first we have used H and CX. Now we are for decoding, we are just reversing it as CX and H. This is how this is the basic, the code for the superdense coding. And then we have to draw the superdense coding circuit. So QC equal to quantum circuit inside we are using two qubits here, Q0 and Q1. And then we are just calling the variables, calling the function name. Create bell pair QC comma 0 and 1. 0 is nothing but Q0 Alice, and 1 is nothing but Bob, Q1. Okay. And then we are using barrier to get the vertical line. We are using barrier just because the circuit becomes more clean and beautiful. More beautiful, we can say it looks very nice, presentation is nice. Okay. And then we are sending message equal to 01. This is the message, this is the classical bit we are sending. And then we are just calling the function name called encode message. And then we are using qubit in this which qubit you are sending 01 message in the qubit 0 na. What is qubit 0? Qubit 0 is Alice. Why Alice? Because Alice is only sending the message. So in the qubit 0 you have to apply this encode message. And then you're sending the message as 0. What message you're sending? 01. And then we are applying again barrier. And then we are decoding the message. Decode message, we are calling the function. So QC comma A is 0 and B is 1. 0 is nothing but Alice and B is nothing but 1. And then we are measuring all, and then we are drawing it. So this is how a circuit looks like. See, this is the same circuit which we have drawn right now. And then we are executing it. Same, we have to run for 1,000 times. We are using Quantum's QASM simulator. So after decoding, after running this Quasm simulator, we will get the output as 10. After running 1,000 times also, we are getting 10 as the output. So yes, that's all about superdense coding. Is there any doubts? I have that's all from my side. Is it okay? Or is there any doubts? Hello?
No doubts, ma'am. From my side, no
Okay.
doubts.
It's clear, ma'am. Yeah.
Okay. Okay. Thank you. And I think Sai will take over.
Yeah, yeah.
Yeah.
Thanks, Shalini.
Thank you,
Like
guys. Thank you. Hmm.
I'll take.
Okay. Okay, Sai. Hmm.
So, is my screen visible? Like, can you see my screen?
Yes, it's coming.
Yeah.
It's visible.
Okay. Perfect. Actually, okay. Let me present my screen. So actually, we should start from universal gates, but due to lack of time, we have only 40 minutes left. So universal gates are not that hard to understand. Maybe if time is left, like I'll cover them at the end. So I'll come back to that if time is sufficient. And also Clifford groups. These are all very basic, and you can easily understand it. So it will not take so much time. Maybe at 10 minutes would be more than enough to explain Clifford gates and universal gates. So firstly, I was thinking of going to the quantum teleportation theorem and no cloning theorem, because both of them are very, very important. As you know, like quantum teleportation is the property that makes quantum computing special from the classical computing. So focusing on what is quantum teleportation and why is it important is very necessary, I feel. So let me first cover no cloning theorem, quantum teleportation, and then if time permits, I'll go to universal gates and daggers and Clifford gates. So what is no cloning theorem? So no cloning theorem, the main agenda of no cloning theorem is to we need to copy a particular state. So that is what the main agenda of no cloning theorem. So for example, there is a painting and you want to have an exact copy of the same painting. So that can never happen, right? Like you can never have an exact copy of the same thing. You can color it, like you can draw a same painting, and then you can like color it with the same colors, but the thickness of those colors, like for example, the thickness of that red that the actual painting has can never be equal to the thickness of the like the painting that you drew. So that is what no cloning theorems, it says that like you can never have an exact copy of the unknown quantum state. And also no cloning theorem, we can have the exact copy, but like the exact copy, you cannot destroy the exact copy, right? So that is why it is very hard to like clone it. So basically the three main principles of no cloning theorem is like superposition, which you already know that like the two quantum states can be like in the same at the same time, can be in the same state at the same time. And also composite systems, which says that like for it is basically the multiplication of product of the superpositions. For example, if you take a box and there is a bomb inside the box and a cat, so what are the possibilities? So it can explode and the cat can be dead, and it cannot explode and the cat can be alive, right? So that is what composite system states that. And transformation distributive says that like any small change in the superposition particles can like affect the both of them independently, affect the both of the particles independently. So that is what no cloning, basically that is what no cloning theorem is like. You cannot have an exact copy of the same quantum state. So like to put it simple, for example, quantum mechanics states that a plus b whole square is a square plus b square plus 2ab, and like no cloning theorem states that a plus b whole square is a square plus b square. But we know that both can never be same. It should either quantum mechanics should be right or no cloning theorem should be right. But like a square plus b square plus c sorry, a square plus a plus b whole square is equal to a square plus b square plus 2ab, right? So like that is why quantum mechanics is right and no cloning theorem can never be like can never be right basically. uh, so let me go to teleportation quickly. So what is teleportation? So we have an information and I want to communicate that information to another person, like wherever he is, like irrespective of the place he might be, irrespective of the distance and irrespective of the place. So we take advantage of two classical bits and an entangled qubit pair. So and then we try to transmit the information that Alice has to Bob. So let us think that the quantum state Alice has is psi each, which is equal to alpha times 0 plus beta times 1. So we are trying to take alpha and beta and communicate it to Bob. So that is the main agenda of teleportation. So please stop me if no cloning theorem is not like if you didn't understand or if you didn't get it, because I was very quick because of the lack of time. So like you can stop and like pause me wherever if something is not clear. So okay, I assume things are clear. So I'm going to yeah. So so basically Telemon, like let us think that Alice, Bob and Charlie, there are three people and Alice wants to communicate the information that he has to Bob. So basically what Charlie, like let us think that Telemon is Charlie for now, because like it's simple ABC. So Charlie creates an entangled qubits and sends one to Alice and one to Bob. So now Alice has some information to send to Bob, and Alice also has a entangled qubit. And then Alice takes help of this entangled qubit and pass on information to Bob. And let's see how he works on this. So there are four main steps basically in quantum teleportation. So first one is Charlie creates a entangled qubits. That is what the first step is, and then Alice applies C naught gate on her two qubits, followed by a Hadamard gate, and then Alice measures the first two qubits and send the outputs to the classical bits. So he basically measures the first two qubits and like he stores that information in the two classical bits. And then Bob applies the transformations. Like we'll see those transformations in the coming slides. Not to worry. And then he depicts the information that are stored in the classical bits. So okay. It's not looking good. Okay, so let us assume that like Alice has a psi state with him. So what he's trying to do is like Charlie will give an entangled pair of qubit to Alice. So now he has an psi state and an entangled state. So he'll calculate the product of it. If you can see here, so he'll calculate the tensor product of it to be precise, and then he'll end up with a state which is represented here. The calculation can be done. I can show it, but just a second. Just a second. It's not the. Yeah. Now it's working good. I'll reshare my screen. Sorry for the disturbance. Okay. So is my screen visible now? Hello.
Yes, yes, I it's visible.
Yeah. Yeah.
Visible,
So
sir.
yeah. So basically now, what do Alice have? He has an entangled pair of qubit that is given by Charlie, and also he has a psi state, which is the state he wants to, like which is the information that he wants to send to Bob. So that is the main agenda of teleportation. So by the end of this quantum teleportation protocol, what we will be able to see is we will be able to communicate this information, that is E equal to 1 by root 2 of 0 0 plus 1 1 to Bob. So that is the main agenda. We'll also code it, and we'll also check, we'll also verify, cross verify whether, like whether Bob has got the right information. So coming to the mathematical part, tensor products and all, I hope you are clear with the tensor products. Like I hope other volunteers have clearly explained, and you are now you already had a good intuition about it. So basically you calculate the tensor product of this psi state, which Alice already has, with the entangled pair, which is 1 by root 2 1 by root 2 of 0 0 plus 1 1, and then you calculate the tensor product of it, and then this is the final output, like output state that Bob has after he gets the entangled pair from Alice. Sorry, after he gets the entangled pair from Charlie. I hope I'm not making things complex. Like, please let me know if, like, because quantum teleportation is like that. Like, like it's quite tricky. So please stop me. Like if you have any doubts, or like anything that's not clear to you. So coming to the second part. So what coming to the second part, second step. So what quantum protocol tells us is like it says us to apply a C0 gate and then a Hadamard gate on the qubits that Alice has. So basically, if you see the like the diagram here. So if you see the diagram here, so basically we then apply a C0 gate and a Hadamard gate to the qubits that Alice has, that is Q0 and Q1. So Q2 is the qubit that Bob has. So now we want to send the information from Q0 to Q2, right? So that is the main agenda of quantum teleportation. So now we will apply C0 gate and a Hadamard gate to Q0 and Q1, and then we will calculate. We already has this state. Has this state, that is psi cross E, and then we take psi cross E. We have Hadamard gate, we have C0 gate, and we already have psi cross E from step 1, and then we calculate the tensor products of all of that, and then we'll end up with a new state, or a new like a new tensor product, basically, which is H tensor product of C0, tensor product of psi, tensor product of E. And then step 3, what it says is like it asks us to measure the Q0 and Q1, and like store that into C0 and C1, which are the classical bits. So for example, Q0, let us say that Q0 ends up to be 0 and Q1 ends up to be 1, and then which states that this is the like which is quite not stubborn, like that is how it is defined. Like if it is 1 1, then the state is psi of 1 minus beta of 0. So if it is psi of 1 minus beta of 0, then we need to apply Z and X gates onto the Q2, and then we will end up the same thing that Q0 has. Let me quickly show you how that works in Qiskit. So what is our main aim? Like we want to uh, send this initial state that is in the purple box to Q2. So Alice has 2 qubits, Q0 and Q1, and Bob has only 1 qubit, that is Q2. So our main agenda is sending the information from Q0 to Q2 using, like the protocols that are suggested by, like by the pioneers and by the scientists. So basically, we have an initial state. We don't create an initial state actually. So we ask the Qiskit to create a random state vector for us. So and Qiskit does it. So it is taking time to compile. Okay. So Qiskit has ended up with this state vector, which is minus 0.2829 minus 0.32i minus 0.172 minus 0.32i. So what we are trying to do is, like, we are trying to convey this information, that is minus 0.2829 minus 0.03i. Sorry, not I. This is as alpha, like we take this as alpha I minus beta I. So then we are also trying to convey this information to Bob. Both of this alpha and beta, we are trying to send that to Bob, is the main agenda of quantum teleportation. So for that, like what the step one, like let's come to step one. So what did it ask? Like the protocol of quantum computing is like, sorry, quantum teleportation is, we first needs to create an entangled pair of qubits and send one to Bob and one to Alice. uh, let's create a, so in the first step we create a bell pair, which is an entangled pair, as Shalini has taught till now. So first we'll create a bell pair, as you can see here, H Hadamard and then a C naught, and then we will send one to Alice and one to Bob. And the third step, sorry, and the second step is, we apply C naught gate on her 2 qubits. Like on her is her represents Alice here. On Alice, 2 qubits followed by a Hadamard gate on Q0. So again, then we will create a C naught gate as suggested by the quantum protocol, and then we will apply a Hadamard gate on Q0. Okay, and then what we will do is, we will measure Q0 and Q1, that are the qubits that Alice has, and then we put them to the classical bits. Like we send the information to the classical bits. So quantum teleportation and no cloning theorem, where the difference comes is, like in no cloning theorem, you cannot destroy the information. Like for example, you cannot destroy the original painting and create a new painting that is exactly same as the original, right? Like there is no chance of destroying the original thing. But here, once you measure the information that Alice has, that is destroyed. So you cannot, you cannot again go back to that. So that is where the main difference comes between teleportation and no cloning theorem. So, and taking this as advantage, you can basically, no cloning theorem and quantum teleportation is basically same, but the only difference is the information is being destroyed in quantum teleportation, and in no cloning theorem, you cannot destroy the information. You cannot destroy the original information, basically. So after you measure the information, or the Q0 and Q1 that Alice has, and store them to two classical bits, then you will apply two if gates that are x and z, that depends upon the output. For example, if you get 0 0, then you will apply an I gate. If the information is 0 1, then you will apply an X gate, and so on. Like if it is 1 0, then you will apply a Z gate, and if it is 1 1, then you will apply a ZX gate. I mean, not ZX, Z and X, both of them you will apply to the Q2. That is the qubit Bob has. So let me run these, and you can we will verify whether, like whether we are getting the same information or not. So the state vector is minus 0.9, minus 0.03i, minus 0.17, minus 0.32i. So we'll keep an eye on this, and then let us create a bell pair first. So that is what quantum protocol says. First create a bell pair and send one entangled qubit to Alice and one to Bob. So first let us do that. So you can see that H and CX, which combines, which gives us an entangled pair or a bell pair, and then we'll apply CX gate and a CX gate and a Hadamard gate to the qubits Alice has got. So we define it as Alice gates, I mean, because those are the these are the gates we are applying to Alice qubits. I mean, the qubits that Alice has got. So we'll apply a CX gate and then a Hadamard gate, followed by a Hadamard gate. And then the third step is we'll measure those. We'll measure those qubits, that is Q0 and Q1, and then sends those qubits to the classical bits, which is basically to store the information. And the important point to note here is like we are destroying the information. Yeah, so the Alice will no longer has the states like minus 0.29 I, sorry, minus 0.29, minus 0.3 I. So this state vector, uh, you basically measure it, so you are destroying the information. So Alice will no longer have that information with her. And then we will apply CX after measuring, after storing that information into the classical bits. What we will do is we will measure those, sorry, we will apply CRX gate, that is controlled RZ gate and controlled Z gate and controlled X gate, based upon the output we get, as I have discussed just a few minutes back. So if it is 00, we'll apply I gate. If it is 01, we'll apply X. If it is 10, we'll apply Z. If it is 11, we'll apply both Z and X. So we'll code it accordingly. I have already coded it accordingly. So I'll run it. And I did nothing, but I added all of these here. Like I just appended all of those steps. As you can see, I also gave barriers. So first we have an initial state. This is the state Alice has got. So it is trying to send this to Q2. That is the main agenda. So Q1 should be equal to Q2 at the end. Like this is initial, and once you measure at the end, so Q2 should be equal to this initial state. For that, what we are doing is like we are following the quantum protocol that is like discovered by the scientists. So I'll run this quickly. Yeah, so I have run that. So now what I'm doing is like I'm sending this circuit to a like a simulator by provided by IBM, and then I'm getting back the result from them, and I'm executing it, and then I'm like getting the result, and then the result has can contain state vectors, and it can contain like Q spheres and everything. But I am interested with the state vector, so I'm getting state vector out of the result, and then I'm printing the result, and then I'm plotting the multi-vector of the result. So basically, if you can see here, let me run this. So now like the main agenda is this initial state should be equal to the output what we get, right? So that is what we are trying to do. So if you can see, so 0 plus 0j and 0 plus 0j belong to the first qubit, that is qubit 0. So what has happened here is like you measured the qubit 0, right? So the information there is has been lost. I mean, you destroyed the information, so there is no information left with Alice now, because you teleported like the information that Alice has got to Bob. So that is what it's I mean, that is how we depict the information here. So 0 plus 0j and 0 plus 0j, which belong to the first qubit, is 0. And then coming to the second, uh, 0 plus 0j and minus, see, this is the same thing that we have, that is the initial state. If you can see, minus 0.928 minus 0.033j, so is what we got here, minus 0.298 minus 0.33j, and then minus 0.172 minus 3.28j, is the initial state of our is the initial state that Alice has got. So it is clear that if you, and also to add a point here, qubit 0 and qubit 1 will always be the same. The only thing that will change is qubit 2. For example, let me quickly run this again. Okay, much time. See, qubit 0 and qubit 1 has always been the same, but the only thing that is changing is Q2, because the information with Alice has been destroyed. Like Alice will no more have the information that Alice has previously had before teleporting the information to Bob. So now Bob has a different now it through quantum teleportation we proved that like the initial state that Alice has been teleported to Bob successfully without like any uh, loss. Basically, like sometimes while teleporting the information we'll have loss, right? So without any loss we have successfully teleported the information that Alice has got to Bob. So is this clear? Like should I explain again, or please ask me if there are any questions.
Yes, sir, it's clear, sir.
Yep. So perfect. Like there are examples like quantum teleportation has been used in many research papers, and they are conducting a lot. It has been used, and it has also been. Scientists are also trying to prove it. Like prove it experimentally. So China has conducted a cutting edge research, and like they try to teleport, and like there are research papers indeed on quantum teleportation. So I'll quickly like maybe I'll quickly walk through again, because quantum teleportation is very important. I'll just explain in brief this time. I'll not take so much time. So the main agenda of quantum teleportation is we want to teleport the information from like from one person to the other person. That is, Alice wants to teleport the information to Bob. Okay. So for that there are 4 steps involved in quantum teleportation. So the first one is we need to create an entangled pair of qubits, that is Q1 and Q2, and then we'll send one to Bob and one to Alice. Okay. And then on the qubits that Alice has got, we'll apply a C0 gate and a Hadamard gate. Okay. And then we'll measure them, and we'll store them in the classical bits, uh, based on the output, that is 00 or 01 or 10 or 11. What we'll do is we'll measure them, and based upon the output we will apply X gate, controlled X gate or controlled Z gate. Okay. If the information is 00, then we will apply an I gate. The protocol is very clear. I mean, the steps are given in the I mean, it's like we should blindly follow it. There is no other way. Like why am I applying X gate, or why am I applying Z gate? Like even I don't know. That's how it worked. Like only if you apply X gate it worked. If you apply some other gate, X gate or T gate, it didn't work. So why we are only going with the next gate and we are applying Z gate? So I hope things are clear, and I'll also share this share this notebook. You can quickly run the notebook and you can check it yourself. And also I will share this mathematics, like the tensor products, the calculation and all of that. So if I wish we had a bit more time, so that like I could have like probably explained these tensor products calculation and all of that. But nonetheless this is very clear. Every step is written. Like maybe you can definitely go through it, and like maybe gain a bit more information from this. So that is what quantum teleportation and no cloning theorem is. So basically no cloning theorem is you cannot create the exact same copy of a qubit state or of a quantum state. Okay, that's what no cloning theorem says. I'm just taking you through it in a very brief way. So let me come to universal gates. So what are universal gates? You can ask me. So let's come to classical computing. So what are universal gates in classical computers? NAND gate and NOR gate are universal gates, right? So why did we choose only NAND gate and NOR gate as universal gates out of AND gate, OR gate, out of all these gate set? Why did we narrowed it down to NAND or NOR? Because using NAND and NOR gates, you can create any gate out of it. Like for example, if you want OR gate, you can use 3-4 NAND gates and come up with an OR gate. If you want an AND gate, you can use 2 to 3 NAND gates and come up with an AND gate. And also an NAND gate and NOR gate combination would result to another gate which you might want. So basically using NAND gate and NOR gate, you can come up with, you can design any gate in classical computers. So the same applies with quantum computers. So universal gates are those gates like which the input can be any arbitrary thing, but the output should be the chosen set. For example, if you want to create an OR gate, so that is any arbitrary gate. You take any arbitrary gate in classical computing, and we will use only NAND gate and NOR gate and bring it to the OR gate. I mean, which is the chosen set. Like that is the chosen gate that we want, right? Like we want an OR gate out of NAND gate and NOR gate. So the same thing happens with quantum computing. So we want, for example, if we want an like any other gate, X gate. So we will use these universal quantum gates and bring an X gate. So that's what universal gates are. It's like same the replica of classical universal gates. So the quantum universal gates are same, but in quantum computing, like Hadamard, phase gate, CNOT gate, and T gate. So basically, U3 gate is defined. U3, U2, and U1 comes under the universal gate set. So U3 gate, which has 3 parameters. These are also called as parameterized gates because they are, like they have the parameters which we can define, and they work as per these parameters that we give to it. So U3 gate is defined. U3 gate has 3 parameters. So why it is defined named as U3 gate, because it has 3 parameters: theta, phi, and lambda. So this is defined by Qiskit. This is how U3 gate is defined. Like there is no other way to talk about this. Like that's how it is defined. And theta lies between 0 to pi, phi lies between 0 to 2 pi, and lambda lies between 0 to 2 pi. So theta, pi, lambda are the rotations around x, y, and z axis. So same goes for U2 gate. So U2 gate can be designed from U3 gate, basically by keeping theta as pi by 2. For example, in U3 gate, if you keep theta as pi by 2, then it is equal to U2 gate. So you can check it for yourself. So only let us take like cos theta by 2. So cos theta by 2. Cos theta by 2. So here theta is pi by 2. So what will we end up with? Cos theta by 2 by 2. So it will be cos pi by 4, which is cos 45. So cos 45 is 1 by root 2. So here if you multiply this 1 by root 2 inside, then you can see it for yourself. So it has become 1 by root 2. So the same goes for the second, third, and fourth elements. So if you put theta by 2 here, and here, then you will end up with U2 gate. So the same goes for U1 gate too. You can literally design U1 gate from U3 gate by taking theta and phi as 0. So basically if you cos 0 is 1, so that is why the first element is 1. And if you apply the same phi and phi as 0 too, then you will end up with U1 gate, which has only one parameter. So why it is named as U1 gate. So, and also if you want to design other gates, for example ZS and T gates, using these universal gates, you can do that too. Like if you take pi as lambda, then you will end up with Z gate. If you take pi as pi by 2, then you will end up with S gate, and if you take lambda as pi by 4, then you will end up with T gate. So all of these all of these parameters, like lambda equal to pi, lambda equal to pi by 2, are very important. And these there are questions asked in the IBM certification exam based upon this topic. Like if you want to design a Z gate using U1 gate, what is the value of lambda? So something like that might be asked. So remember, we just need to remember this, that there is no other way for this. So I'll quickly walk you through Clifford groups and Clifford group and daggers. So basically, what is a dagger is a Hermitian conjugate of a gate. For example, S dagger is the Hermitian conjugate of an S gate. So what is an Hermitian conjugate? So we first calculate the complex conjugate of each element. Like for example, if it is a 2 by 2 square matrix, then you calculate the complex conjugate of each element, that is 1 1 1 2 2 1 and 2 2, and then you calculate the transpose of this whole complex conjugate matrix. So then you will end up with a Hermitian conjugate. So what is a Clifford gate? So Clifford gate is, like for example, there are poly gates like X gate, Z gate, H gate, all of that. Then if you can bring up another poly gate using these polygates, then it is called as a Clifford gate. So the property of transforming polys into other polys is called a Clifford gate. So for example, if you check here, so H gate, X gate, and H gate will give a Z gate. So you are transforming two polys into another poly, like you are taking help of two polygates, and then you are calculating, and you are constructing another polygate. And also here, like H, Z, and H gate will give you an X gate. So basically, those are examples of these Clifford group gates. And like this Hermitian conjugate, as I have explained, you first need to calculate the complex conjugate of the matrix, and then you need to transpose it. So, and also these are also Clifford group gates, because like you are taking the polygates and designing another polygate. So S, X, and S dagger will give you an Y gate. All of these are very important. Like I have given the quantum developer exam, and like these were the questions that are asked there. So remembering all of these are very important, because you will lose marks if you don't remember these in the exam. So examples of single qubit Clifford gates, here we used H, X, and H to Z. Now if you use Z, X, and Z, you will end up with minus X. So like all of there are so many examples like this, like ZXZ and HZH. All of these we need to remember if you want to crack the exam. There is no other way. So yeah, so these are all single qubit Clifford gates. And coming to the multi-qubit Clifford gates, so they also transform, and same thing happens with the multi-qubit Clifford gates too, but they use two qubits, and single qubit Clifford gates use only single qubit. So the best example of two qubit Clifford gate is a C0 gate. So because it takes two qubits and it transforms the qubits to these poly states to polygates to the other gate. So non-Clifford gates do rotation, and the three axes are non-Clifford gates do not convert polygates. Polygates to other polygates. They do only rotation. For example, RX gate, RY gate, and RZ gate are called as non-Clifford gates, because they don't have the property of converting one set of Clifford gates to the one set of polygates to the other set of polygates. So that's why they can only do rotation. They cannot transform from one polyset to the other polyset. So why we call it non-Clifford gates. I quickly quickly walk you through, like please don't mind. And if you have any query, please rise up, like I'll be very happy to answer. I just want you to understand teleportation rather than these universal gates, because quantum teleportation and no cloning theorem is very important, as in the further when if you want to explore quantum computing further, like both of them, like quantum teleportation and no cloning theorem are very important. So I'm stressing it again and again. Like if you have any doubt on quantum teleportation, like please rise up. I'll be very happy to answer. So I assume everything is clear, like, or click along. Is it clear, or should we, like what? If there are any doubts, please rise up.
I think it's clear, sir.
Okay. So that is the end of the session. I'll send the code for quantum teleportation, and also I'll send the notes. Maybe you can walk through that, and like if you have any query, please don't mind to ask it on whether on Discord or on WhatsApp. Anything is fine for us. Like we volunteers will be very happy to help.